Hello students, welcome to EPG Pathshala. I am Anshul Gupta, lecturer from Delhi Pharmaceutical Sciences and Research University, Delhi. Today we are going to discuss module Drying Technology under paper Product Development Part 1. Learning objective for this module will be, first of all we will learn about fundamental of dryings, behavior of solids during drying, classification of dryers and application of dryers in the field of pharmacy. Now first we will understand what is drying. It is removal of a liquid from a material by the application of heat and is accomplished by the transfer of a liquid from a surface into an unsaturated vapor phase. Drying is generally thermal but could be non-thermal also, like adsorption, absorption and desiccation, etc. Drying can serve the following purposes. First, preparation of granules for tablets, capsule or bulk dispensing. Second, it can be used for the preparation of products like dried aluminum hydroxide, spray dried lactose, etc. Third, it reduces the microbial growth in plant and animal extract. Fourth, drying before milling aids comminution as dried material is comparatively more friable. Fifth, the ease of handling and transportation as dried product is less in weight and bulk. With the drying, stability increases as compared to the moist material, for example aspirin, penicillin, ascorbic acid, etc. Now we will discuss theory of drying. Drying involves two processes, heat transfer and mass transfer. For heat transfer, latent heat is given for vaporization of moisture during drying. There is a thin film of liquid at the surface of material to be dried that needs to be evaporated. The rate of evaporation of this film is related to the rate of heat transfer given by the equation dW by d theta is equal to K by lambda, where dW by d theta is the rate of evaporation pounds of water per hour, Q is the rate of heat transfer, lambda is the latent heat of vaporization of water. Secondly, mass transfer is involved in diffusion of water through the material to the evaporating surface and then to the vapor state into passing air stream. The driving force for the mass transfer is humidity difference. The rate equation for the mass transfer is given as dW by d theta is equal to K prime A difference of Hs minus Hg, where dW by d theta is the rate of diffusion expressed as pounds of water per hour, K prime is the coefficient of mass transfer, A is the area of evaporating surface in square feet, Hs stands for absolute humidity at evaporating surface, Hg is absolute humidity in passing air stream. After an initial period of adjustment, the rate of evaporation is equal to the rate of diffusion of vapor and the rate of heat transfer can be equated with the rate of mass transfer. So, the equation will become dW by d theta is equal to K by lambda or is equal to K prime A Hs minus Hg, where Q is expressed as the sum of the rates of heat transfer by convection, radiation and conduction. So, the equation can be expanded as dW by d theta is equal to Qc plus Qr plus Qk upon में lambda is equal to K prime A Hs minus Hg. The rate of drying may be accelerated by increasing any one of the individual terms in above mentioned equation. The rate of convection heat transfer Qc can be increased by first increasing the airflow rate, second by raising the inlet air temperature. The rate of radiation heat transfer QR can be speeded up by first introducing high temperature radiating heat source into the drying chamber. The rate of conduction heat transfer Qk can be stepped up by reducing the thickness of material being dried. Second, allowing it to come in contact with raised temperature surface. Third, increasing the air velocity also speeds up the rate of drying by increasing the coefficient of mass transfer. Fourth, dehumidifying the inlet air thus increases the humidity differential. Now we will discuss behavior of solids during drying or rate of drying. The rate of drying of a sample can be determined by suspending the wet material on a scale or balance in a drying cabinet and measuring the weight of sample as it dries as a function of time. The figure shows drying rate by plotting moisture content versus time. The changes taking place may be seen more easily if the rate of drying is calculated and plotted against the moisture content as shown in figure B. Comparison of the rate of drying curve with the drying time curve is clarified when the moisture content is plotted in reverse order, that is with the high values to the left. Now we will see the graph and try to understand it. Segment AB is the initial adjustment. When a wet solid is first placed in a drying oven, it begins to absorb heat and increases in temperature. At the same time, the moisture begins evaporating and thus tends to cool the drying solid. After a period of initial adjustment, the rate of heating and cooling becomes equal and the temperature of drying material stabilizes. This period of initial adjustment is shown in segment AB in the figure A and in the figure B. Now we will discuss segment BC, that is constant rate period. At point P, the temperature is stabilized and remains constant as long as there is a film of moisture remaining at the surface of the drying solid. Between point B and C, the moisture evaporating from the surface is replaced by the water diffusing from the interior of the solid at a rate equal to the rate of evaporation. The rate of drying is constant and the time BC is the constant rate period. Now talking about point C, that is critical moisture content. At point C, the surface water is no longer replaced at a rate fast enough to maintain a continuous film. Dry spots begins to appear and the rate of drying begins to fall off. The moisture content at which this occurs is referred to as critical moisture content. Now talking about segment CD, it is known as first falling rate period. At and below the critical moisture content, the movement of moisture from the interior is no longer sufficient to saturate the surface. Between point C and D, the number and the area of the dry spots continue to grow and the rate of drying falls steadily. The time CD is referred to as the first falling rate period or the period of unsaturated surface drying. Since the surface is no longer saturated, it tends to rise above the wet bulb temperature. Now segment DE, it is second falling rate period. At the point D, the film of surface water is completely evaporated and the rate of drying depends on the rate of diffusion of moisture to the surface of solid. Point D is referred to as second critical point. Time DE is called the second falling rate period, during which the surface temperature approaches the temperature of drying air. Now talking about point E, it is called equilibrium moisture content. At the point E, the drying rate is equal to 0 and the solid is in equilibrium with the surrounding. That is, its temperature and moisture content remain constant. Continue during drying after this point is a waste of time and energy. Thus, from previous learning, we can define certain terms like equilibrium moisture content, equilibrium relative humidity and water activity. Now first we will talk about equilibrium moisture content. The moisture content of a material that is in equilibrium with an atmosphere of a given relativity is called equilibrium moisture content of the material. At equilibrium moisture content, there is no driving force for mass transfer since the material exerts a water vapor pressure equal to the vapor pressure of atmosphere surrounding it. Now equilibrium relative humidity. It is the relative humidity surrounding a material at which material neither gains nor loses moisture. At a given temperature, the equilibrium relative humidity for a material is determined by its moisture content, just as the equilibrium moisture content is determined by the surrounding relative humidity. Lastly, talking about water activity of a material is the ratio of water vapor pressure exerted by the material to the vapor pressure of pure water at the same temperature. Pure water is assigned an AW of unity equivalent to equilibrium relative humidity of 100%. Drying of solids. The moisture in a solid can be expressed on a wet weight or dry weight basis. According to wet weight basis, the water content of a material is calculated as a percentage of the weight of the wet solid, and dry weight basis, the water is expressed as a percentage of the weight of the dry solid. Now, loss on drying. It is expression of a moisture content on a wet weight basis, which is calculated as follows. Percent loss on drying is equal to weight of water in sample divided by total weight of wet sample into 100%. Now, what is moisture content? Another measurement of moisture in a wet solid is that calculated on a dry wet basis. This value is referred to as moisture content, expressed as percent moisture content is equal to weight of water in sample divided by weight of dry sample into 100. Now, types of solid on the basis of drying. These are of two types, crystalline and amorphous. In crystalline, water is held in shallow pores and interstitial spaces. For example, zinc oxide, magnesium oxide, etc. In amorphous solids, moisture is an integral part of molecular structure and physically entrapped in fine capillaries and small interior pores. For example, starch, casein, yeast, insulin and aluminium hydroxide. Thus, amorphous solids are difficult to dry than crystalline solids. Now we will discuss about dryers. Dryers may be classified in several different ways depending on the method of heat transfer, that is conduction, convection and radiation, or solid handling depending on the nature of material, agitation requirement, etc. Classification based on the methods of solid handling as per agitation requirement is shown schematically in the figure being shown on the screen. Dryers are first divided into two types, material not agitated and the one which agitate the material. Now, materials not agitated is of static bed dryer. Static bed dryers are again of two types, batch type, continuous type. Example of batch type are tray and truck dryer, vacuum self dryer, freeze dryer. Example of dryers in continuous type are tunnel dryer, belt dryer, festoon dryer, drum dryer. Now, dryers as per material agitated. These are of three types, moving bed dryer, fluidized bed dryer, pneumatic dryer. Moving bed dryer are again classified as batch type and continuous type. In the batch type, the example of dryers are vacuum tumble dryer, pan dryer. In continuous type, the example of dryers are rotary dryer, turbo tray dryer, vibrating conveyor dryer, tower and cascade dryer, screw conveyor dryer. Now, talking about fluidized bed dryer, these are again of two types, batch type, continuous type. Example of batch type is vertical dryer. Continuous type example are horizontal vibrating conveyor dryer, vertical dryer. Under pneumatic dryer, continuous type is present and the example of dryers are spray dryer, flash dryer. Now, we will discuss about static bed dryers. These are the systems in which there is no relative movement among the solid particles being dried, although there may be a bulk motion of the entire drying mass. Only a fraction of total material of particle is directly exposed to heat source. The exposed surface can be increased by decreasing the thickness of the bed and allowing drying air to flow through it. Now, we will discuss freeze dryer. Freeze drying is also called lyophilization, glaciation or drying by sublimation. It is used for drying heat sensitive material. It is used for drying material which is easily attacked by oxygen. Example of the materials being dried by freeze dryer are blood serum, plasma, antibiotics, hormones, bacterial cultures, vaccine and many foodstuffs are dehydrated by freeze drying. Principle: freeze drying depends on the phenomenon of sublimation, whereby water passes directly from solid state, that is ice, to the vapor state without passing through the liquid state. Sublimation can take place at pressures and temperature below the triple point, that is 4.579 mm of Hg absolute and 0.0099 degrees Celsius. The water in pharmaceutical products intended for freeze drying contains dissolved solids, resulting in a different pressure temperature relationship for each solute. In such cases, the pressure and temperature at which the frozen solid vaporizes without conversion to a liquid is referred to as eutectic point. Freeze drying is carried out at temperatures and pressures well below this point to prevent the frozen water from melting, which would result in frothing as the liquid and frozen solid vaporizes simultaneously. In actual practice, freeze drying of pharmaceutical is carried out at temperature of minus 10 degrees Celsius to minus 40 degrees Celsius and at pressure of 2200 microns. Now requirements for freeze drying. Freeze drying must meet the three basic requirements for all types of drying despite this unusual approach to drying. First, the vapor pressure of the water on the surface of the material being dried must be higher than the partial pressure of the enveloping atmosphere, that is, there must be a positive vapor pressure driving force. Second, the latent heat of vaporization must be introduced to the drying solid at such a rate as to maintain desirable temperature levels at both the surface and interior. Third, provision must be made for removal of the evaporated moisture. Now we will discuss components of a freeze dryer. Freeze dryers are composed of four basic components. First, a chamber for vacuum drying. Second, a vacuum source. Third, a heat source. And fourth, a vapor removal system. Vacuum is achieved by pumps, steam injectors, or a combination of the two. Heat is provided by conduction or radiation or by both. Three different methods for the removal of water vapor are employed: condensers, desiccants and pumps. The water vapor is removed from the drying chamber and condensed in the form of a thin layer of ice on a heat transfer surface in the condenser. The ice is removed intermittently by melting it with a heated fluid that is circulated through the condenser, or in the case of a continuous operation, by means of a scraper blades. Liquid or solid desiccants are often employed in the initial vapor removal to enhance the efficiency of the pumps removing the water vapor. In general, scraper blades and desiccants are used for freeze drying large volume biologicals like serum, penicillin, and usually are not used for preparing pharmaceutical dosage form. The different stages of freeze drying are: first, pre-freezing. Material is frozen by keeping the material below or at minus 20 degrees Celsius. Pre-freezing the material before application of vacuum avoids foaming. Second, vacuum. Rotary pumps on small scale and ejector pumps on large scale are used to reduce the pressure sufficiently. Third, primary drying. During primary drying, the latent heat of sublimation must be provided and the vapor removed. Primary drying stages by sublimation can remove the unbound water. Secondary drying. It is used to remove bound water or traces of water left after primary drying. The temperature is raised up to 50 degrees Celsius, or desiccant is used to carry secondary drying. Now we will discuss moving bed dryers. These are the systems in which the drying particles are partially separated so that they flow over each other. Motion may be induced by either gravity or mechanical agitation. The resultant separation of particles and continuous exposure of new surfaces allow more rapid heat and mass transfer than can occur in static beds. Under moving bed system, now we will first discuss vacuum tumble dryer. The most common shape of the tumble dryer is the double cone vacuum dryer. Vacuum dryer is rotated at a speed of 6 to 8 rpm and the vacuum is maintained with low temperature drying. Heat is supplied to the tumbling charge by contact with the heated shell and by heat transfer through the vapor. Heating fluid circulates through a jacket and enters and exits through a dynamic seals along the axis of rotation. Indirect methods rely on contact between wet material and the jacketed walls of the dryer to supply energy, and the drying rate can be heat transfer limited. The ratio of jacket area to the working volume tends to decrease with increasing size. So, large models often require additional internal plates or pipe coils to increase available area for the heat transfer. Some materials such as waxy solids cannot be dried by this method because the tumbling action causes the material to aggregate into balls. Now come to the fluidized bed dryers. These are the systems in which the solid particles are partially suspended in an upward moving gas stream. The particles are lifted and then fall back in a random manner so that the resultant mixture of solid and gas acts like a boiling liquid. The gas-solid contact is excellent and results in better heat and mass transfer than in static and moving beds. Now talking about principle. Here the gas is allowed to flow upward through a bed of particulate solid at a velocity greater than the settling velocity of particles. The solids are buoyed up and become partially suspended in the gas stream. The resultant mixture of solid and gas behaves like a liquid and the solids are said to be fluidized. The fluidization technique is efficient for the drying of granular solids because each particle is completely surrounded by the drying gas. In addition, the intense mixing between solid and gas results in uniform conditions of temperature, composition and particle size distribution. The fluidized bed dryers are available for use in pharmaceutical industry are of two types, vertical and horizontal. The fluidizing air stream is induced by a fan mounted in the upper part of the apparatus. The air is heated to the required temperature in an air heater and flows upward through the wet material, which is contained in a drying chamber fitted with a wire mesh support at the bottom. The airflow rate is adjusted by the means of a damper and a back collector filter is provided at the top of drying chamber to prevent carryover of the fine particles. The unit described is a batch type dryer and the drying chamber is removed from the unit to permit charging and dumping. Because of short drying time and excellent mixing action of the dryer, no hot spots are produced and higher drying temperatures can be employed than are used in conventional tray and truck dryer. The unit as shown on the screen is designed for the direct preparation of tablet granulations as well as for the drying of conventionally produced wet granulations. Advantages of vertical fluidized bed dryer. It has short drying time, it provides excellent mixing action of the dryer, no hot spots are produced, higher drying temperatures can be used, it can be used for both dry and wet granulation process of tablet manufacture. Now we will discuss horizontal vibrating conveyor dryer as shown on the screen. The heated air is introduced into a chamber below the vibrating conveying deck and passes up through the perforated conveying surface through the fluidized bed of solids and into an exhaust hood. A fluidized bed of uniform density and thickness is maintained in any given drying zone by the vibration. Residence time in any drying zone is controlled by the length of the zone, the frequency and the amplitude of vibration and the use of damps. The dryer can be divided into several different zones with independent control of airflow and temperature, so that drying can take place at the maximum desirable rate in each stage without sacrificing the efficiency or damaging heat sensitive materials. Now coming to pneumatic dryers. These are the systems in which the drying particles are entertained and conveyed in a high velocity gas stream. Pneumatic systems further improve on fluidized beds because there is no channeling or short circuiting of the gas flow path through a bed of particles. Each particle is completely surrounded by an envelope of drying gas. The resultant heat and mass transfer are extremely rapid, thus drying times are short. Now under pneumatic dryer we will discuss spray dyers. Its principle is they can handle only fluid materials such as solutions, slurries and thin paste. The fluid is dispersed as fine droplets into moving stream of hot gas where they evaporate rapidly before reaching the wall of drying chamber. The product dries into a fine powder which is carried by the gas current and gravity flow into a collection system. The surface liquid is quickly evaporated and a tough shell of solid is formed. As drying proceeds, the liquid from the interior of droplet diffuses through this shell. The diffusion of the liquid occurs at a much smaller rate than does the transfer of heat through the shell to the interior of the droplet. The internal heat and pressure causes the droplet to swell and the shell becomes thinner. If the shell is non-elastic or impermeable, it ruptures, producing either fragments or bud-like forms on the original sphere. Thus, spray dried material consists of intact spheres, sphere with buds, ruptured hollow sphere or sphere fragments. Now we will discuss the spray dryer being shown on the screen. A spray dryers usually have the following components: feed delivery system, atomizer, heated air supply, drying chamber, solid gas separator and product collection system. Now we will discuss its working. The feed is delivered to the atomizer by gravity flow or by the use of a suitable pump. Spray dryer atomizers are of three basic types: pneumatic atomizer, pressure nozzle and spinning disc atomizer. In pneumatic atomizer, the liquid feed is broken up into droplets by a high velocity jet of air or other gas. It is mainly used for viscous liquids which are fed by pressure nozzles under high pressure and is broken up by coming into contact with air or by impact on another jet or fixed plate. In spinning disc atomizer, the liquid is fed to the center of a rapidly rotating disc where centrifugal force breaks the fluid up into droplets. Separation of solid product from the effluent gas is usually done by cyclone separator, also referred as the primary collector. The dyed product collected at this point is called cyclone product. Any dust remaining in the air may be removed by means of a filter bag collector or a wet scrubber to avoid air pollution. The product reaching the walls of a drying chamber is called chamber product, which is removed at the bottom of the chamber. The final dyed product is generally a mixture of both the chamber and cyclone products. Spray drying finds a great utility in the pharmaceutical industry because of the rapidity of drying and the unique form of the final product. There are three major uses for the spray drying process. First, drying heat sensitive material as they are dried in fraction of seconds due to increased surface area and rapidly removed to prevent over drying. Second, in tablet and capsule manufacture, as the spherical particles which are more uniform in shape and size produce better flow. Third, encapsulating solid and liquid particles as the solvent is evaporated, the coating material envelopes the suspended particle. The coating provides such a valuable characteristics as taste and odor masking, improvement in stability, enteric coating and sustained release. Oily liquids may be encapsulated by emulsification in water with the aid of a gum such as acacia or starch and subsequent spray drying. As the water evaporates, the oil is entrapped in shell of gum. This process is used for the preparation of dry flavor oils. Lastly, we will discuss microwave drying, which is the most common method used for drying. Energy in the form of microwave is converted into internal heat. The heating effect is produced by the interaction of a rapidly oscillating electric field with the polarized molecules and the ions in the material. The interaction of the alternating field with the ions causes a billiard ball like collision with unionized molecules and the impact energy is converted into heat. A given material's molecular and ionic makeup intimately affects its ability to be dried, as is shown in the power conversion equation for microwave heating. This equation is being shown on the screen, where P is the power developed, K is the constant, F is the frequency, E is the electric field strength, epsilon prime is the relative dielectric constant of the material being heated, tan delta is the loss tangent or dissipation factor of the material, epsilon double prime is the loss factor of the material. So, the advantages of microwave drying are: they allow drying at low ambient temperature, avoiding case hardening. Microwave vacuum drying can be used for thermolabile materials such as vitamin, enzymes, protein and flavors. Extremely efficient energy utilization and energy saving as much as 70% have been realized in industrial installations by use microwave drying. Thus, by the end of this module, we have come to learn about the basic of drying, various dryers, their application and contribution in pharmaceutical industry. So, I hope this lecture will be a useful one for all of you. Thank you, students.